Right. Okay, now that we're recording. Welcome to the Air Sea Fluxes from Space webinar series. Today we have Shikhar Rai, who's a postdoc at Woods Hole Oceanographic Institution. He was before that a graduate student at the University of Rochester. And he's going to talk about atmospheric wind energization of ocean weather. Shikhar is about 1.5 years into his postdoc, and he's currently looking for a next postdoc. So take it away, Shikhar.
Thank you, Sarah. And thank you everyone for being here to listen to my talk. This is one of the work that I did during my PhD with Tom and my advisor Hussein at University of Rochester. And the title is the same title that we just published a paper on. And yeah, so today I'm going to talk about how the wind forces the ocean mesoscales. And here the ocean weather just means mesoscales. Um, so let me start. Okay, why is this? Okay, let me start with the introduction. So we know that the wind is the net source of energy for the ocean. And the ocean gets almost about 1 terawatt of energy. So this is a figure from Hughes and Wilson 2007, where they calculated total wind work from the QuickScat and altimeter products and found that around 760 gigawatt of uh, uh, energy is input into the ocean. And uh, I guess the audience in this webinar knows that the mesoscale eddies lose energy to the wind. So this is the wind work to the eddies. So in this works, we had all explicitly detected the closed contours of the SSH anomalies and calculated the wind work on them and found that there is 27.7 gigawatt of energy taken away from these mesoscale eddies. This losing of energy by the mesoscale eddies, the wind is attributed to the eddy killing. And the explanation, so in this finding, in this talk, I'll be trying to show that in addition to the ocean eddies, the ocean strain also lose energy to the winds and air breeze. And this depends on the direction or the orientation of the both wind stress and ocean current. And the ocean strain or the ocean eddy can also gain energy, not just lose energy to the winds. So before that, let me briefly discuss about how the ocean eddy loses energy to the wind. So let's imagine there is an eddy rotating counterclockwise, and there's a constant wind over it, but the wind stress depends on the relative winds. Therefore, the relative winds look like this. It will be larger to the side where the winds and ocean currents are in the opposite direction, and it will be in the same direction when the winds and ocean current uh, are the same. So this will cause negative but larger wind work at this region where the winds and ocean current are opposite, but smaller and positive wind work where the winds and ocean current are in the same direction. So this will result to the net negative wind work over this whole eddy, which is called eddy killing. But we can give the same arguments about the ocean strain. The same thing applies. Let's imagine there is a ocean strain like this. And since the wind stress is again dependent on the relative winds are larger in the region wherever the ocean currents and the winds are opposite, and smaller in the region where they are same. So we'll get the same thing like in ocean eddy, and if we integrate over this whole straining region, we'll see that the ocean strain also loses energy to the winds. So this is our finding in this paper, and I'll be showing you how we can get this wind work to the eddy part and the strain part individually. So to do this, we use a framework called coarse graining framework. It's a multi-scale analysis framework. So this is a framework that I use to divide scales. So in this scale, what we do is we choose a length scale L, and this length scale separates the large length scale and large scales and smaller scales. So this is just done through a convolution of the original field, any field, velocity, stress. So, and this GL is the kernel that we use for the convolution. And we get the low pass filtered field U bar, which is the large scale values. And the smaller scale part is just the subtraction of the original field minus this low pass filter field. So this is a technique widely used in LES literature. And in this framework, we can define large-scale products like this. In the Reynolds averaging, when we have large-scale defined as the product of these ensemble averages. In the coarse graining, we have the product between the low-pass filtered fields. Similarly, the small-scale fields can be represented in this way here. And we can also get the spectra from coarse graining framework like this. So in the Fourier space, the coarse graining spectra is like this. And in the coarse graining framework, this can be obtained from this expression that I'm showing here. Now, a question that I have come across many times whenever I talk about coarse graining is what is the difference between the regular spatial filtering and coarse graining? So the difference is the commutation of derivatives with the filtering operation. So because the Earth is a sphere, and if we apply a regular spatial filtering, we'll get a numerical artifact that will cause errors. So here on the left, I'm showing you the result after coarse graining. So I had an original field of non-divergent field, which after filtering became divergent. So everything seeing here that you're seeing here is the error that's coming from the numerical artifact. But the coarse graining technique that Hussein developed is it commutes with the derivative operation. So there is no error from the numerical artifact. So because of this, now we have energetically consistent equations. We can write equations in coarse graining framework for large scales and small scales. Now, we have this framework. How do we define the windwork, 2ADs, and strain individually? So to do that, what do we do first is we take the windwork to scale smaller than L using a coarse graining framework. This is from one of the work that we did. And in this coarse graining framework, we defined any windwork that is on the scale smaller than our chosen length scale L is given by this expression EP. From here on, what we do is we invoke ultraviolet scale locality from Inc. 2005. It's just an argument that tells that the most everything beyond the chosen scale could be inferred from the resolved scales. And then we use multi-scale expansion, and we get a first order approximation of this EP as EP tilde. And we get the expression for EP tilde like this. Now, what we see here is that we have a gradient of wind stress and gradient of ocean currents here. And what we can do from here is we can break the gradients of the wind stress and the gradients of the ocean current individually to symmetric and skew symmetric part. And if we rewrite this, we'll get the expression for EP, the EP tilde, as the sum of these two things here. And these two things are here on the first term is the wind work and strain, and the second term is the wind work and vorticity. So now, first I'm going to show you how good is the approximation EP to EP tilde. So here on the left, using QuickScat and altimeter data, I'm showing you how this approximation looks like. On the left-hand side is the truth, and on the right-hand side is our approximation. And here we can see that it has a pretty good correlation with uh, Pearson's correlation coefficient 0.88 and goodness of fit 0.78. Similarly, from the CSM with high resolution CSM simulations, we get a very good correlation from high resolution simulation as well. Here we have even better. The Pearson correlation coefficient is 0.91, and the goodness of fit is also 0.83. So in the average field, if we look, this is from the 7-year, 8-year average data for the whole QuickScat period. And this is the truth, and this is the first order approximation. And similarly, from the CSM, we get a very good correlation between our first order approximation and the truth. And from the time series, so here what I'm showing you is the time series of the EP for 8 years from QuickScat data. This blue line is our truth, and the orange line here is the first order approximation EP tilde. And we see that it is very nicely correlated with the truth. And similarly in the ACC, it has slight offset, but even then we have a very good correlation. And on the right-hand side, what I'm showing is the average correlation coefficient at every grid point. So this is the correlation that I took for all of the 8 years data, and we can see that the correlation is very good at almost every point in space. And this is the same plot using CSM data, and we see a very good correlation from CSM high resolution simulation as well. So from this, we can say that the approximation that we obtained using Ein's ultraviolet scale locality and multigradient expansion is a very good approximation for the truth EP. Now, what we can do from here is we can break this EP tilde to windwork to strain vorticity, like I showed you in the previous slide. So if we plot that, what we can see is the vertical part of the windwork is very nicely concentrated in the regions wherever there is high vorticity. So this is the lines are the streamlines of the ocean currents. This blue and red are the windwork. And for the strain part, what we can see is it's concentrated in the regions wherever there is strain, like here in the saddle points. So we can see that our decomposition of the windwork and vorticity and strain is nicely seen in this plot. Similarly, if we look from the satellite data, high resolution CSM data, we can see the same thing. It's concentrated in the eddies for the vertical and concentrated in the saddle points for the strain. Now, if we average it over the 8 years, what we'll see is the windwork on the eddies and windwork on the strain is equal. So this is also true from the high resolution simulation data. The windwork on the vorticity and windwork on the strain are equal. So the next thing that we saw in this work is also that because the gradients in the stress is not only because the stress is dependent on the relative winds, but the gradients and the stress may also be there because there is gradient in the wind itself. So wherever there is gradient in wind, there is gradient in stress. So imagine that this is the gradient in stress that is coming from the gradients of winds. we can break this into large scale winds like this, and small scale winds. So this total wind stress is the sum of large scale winds and small scale winds. Now, the small scale wind stress gradients can be broken into the vertical wind stress gradients. Here in this case, the anti-clockwise call of the wind stress, and the strain. So in this case, it's stretching in this minus 45 degrees and converging in about positive 45 degrees. So where does this happen? This we can see from the westerlies and the easterly trade winds. So in this case, the subtropical Z, the westerly subtropical Z and easterly trade winds will cause a clockwise call of wind stress gradients in the northern subtropics, while in the southern it will generate a positive curl. So in the similar way, for the strain part, we'll get the direction or the orientation of the wind stress gradients, the straining part of the wind stress gradient, aligned in this fashion. So the result of this is seen in the wind work on the mesoscales. So if we, sorry, let me again come to this part here. Again, this EP tilde can be rewritten in the form of the contribution from the inherent gradients in the winds and in the induced wind stress, that is because of the relative winds. So here on the right hand side, this part is the effect of the wind stress gradients that are induced by the ocean currents, because the wind stress is uh, relative to the comes from the relative winds. Well, this part is the one that is coming from the gradients that are already present in the winds. So now I'm going to show you the effect of this inherent gradients of the winds that results from this alignments of the background winds in the atmosphere. So here I'm showing you the wind work on the negative ocean vorticity only. So I masked out all of the regions where the ocean has positive vorticity. So I chose only the only the regions where the ocean have positive vorticity, and then calculated the wind work and averaged it over the 8 years. And this is the plot of the wind work on the vorticity. So, and this is the plot of the curl of wind stress. What we can see here is whenever the, uh, oh, I think I chose the opposite plot here. Yeah, so what we can see here is whenever this ocean current is, I think I chose the opposite one. Whenever the vorticity and the ocean current are opposite to each other, it will result in the negative values. And whenever there is the value of this, the orientation of this curl is opposite to each other, we'll have the positive wind work on this vorticity. And this will also appear in the wind stress gradients as well. So if we choose, okay, here this one is the correct orientation. So when we choose, so here I chose the orientation of the oceanic flow wherever the oceanic strain are aligned in this direction. And because the atmospheric wind is aligned in this way. The strain in the atmospheric winds are aligned like this. So whenever these two directions matches, we have positive wind work. And whenever these two are in opposite direction, we get the negative wind work. So this is coming from the background gradients of the symmetric part of the wind stress gradients. So we see positive wind work in this direction and negative wind work in this direction. Now, the summary is that there is um, gradients in the wind stress. One is because of the ocean current, because wind stress is relative to the ocean current. And second is because the the winds inherently have gradients in them. So these gradients can be broken down into symmetric and skew-symmetric parts. And these symmetric and skew-symmetric gradients in the winds act on the vorticity and strain of the ocean and injects energy or removes energy from them. So the wind stress gradients that arise because of the imprints of the oceanic currents and the wind stress, or because of the relative component, is always acting to remove energy from the ocean mesoscales, while the wind stress gradients that are coming from the inherent gradients of the wind will inject or remove energy from the ocean of vorticity or strain, depending on how the alignment of these two gradients, the gradients in wind stress and the gradients in the ocean current are. So these are the main findings from our work. And with this, I would like to end my presentation. This is the paper link that's here, and this is the link to my website. And I'm also looking for a second postdoc in Edge Interactions. If you have any such questions, please let me know. Thank you.
Well, thank you. This is great. Questions for Shikhar? And maybe while people are thinking about questions, I'll go back to something you showed at the beginning. You showed the correlation between your full estimate for EP and your coarse-grained approximation. And you showed that in the ACC, there was an offset.
Yes.
And I wonder, what causes the offset? Does it matter?
Yeah, so the argument for this decomposition is that this becomes more accurate in the region where the slope of the spectral slope of the wind stress and ocean currents are both larger than -1. So if the slope is more steeper or equal or more steeper than -1, then this ultraviolet scale locality is more applicable. But in the Southern Ocean, because the size of the eddies, because of this deformation radius, we have spectral peak at more smaller wave number. So I'm sorry, more larger wave number or smaller scales. Then this will start to deviate away. So this is applicable only wherever the spectra is steeper than -1, and is also applicable to submesoscales. Yes, so because our filter length that we chose is 100 kilometer, maybe at the ACC, the effect of this scale locality is not applying very well.
Does that have implications for thinking about how you apply this globally?
Yes, so we have to be careful whenever we are applying this globally. So uh, we should choose a length scale if we are approximating the wind work to the scales smaller than any scale L, then we have to make sure that we're only looking at the scales that is at higher wave number than the spectral peak.
Other questions? Nobody's bursting with other questions. I'll ask about the implications for satellite observations.
Yeah, I think it's so one of the things that I find interesting from this work is that the wind work is there is wind work on the strain part as well, like eddy killing.
Mhm,
There is counterpart, strain killing.
mhm,
So as we go to smaller scales, we are the next generation satellites is trying to look into more smaller scales, more higher resolutions. The fronts get stronger in these regions. There is
mhm,
higher value of divergences and convergences at smaller scales. It will be interesting to see if there's equal distribution of the wind work on strain and vorticity will still hold there, or what kind of mechanisms, what kind of atmospheric scales, and what kinds of oceanic scales are coming into play in the
mhm.
evolution of these fronts. So that would be, I think, interesting to look into. And the other thing is, we have been depending on the correlation coefficients to look into wind work. So that's it's a very nice way of looking how the ocean and atmosphere is interacting. But using there is a limitation to using correlation coefficient because it does not directly fit into the energy equations or the physics the equation of the physics. So using this framework, what we can do is we can directly put this in the equations of the physics. For example, we can put this in the equation of turbulent kinetic energy, and then see how this turbulent kinetic energy is evolving, and we can look into how the strain part and the vorticity part is evolving and what is happening to this kind of vorticity and fronts and divergences. So yeah.
Yeah. So one of the interesting things about scales is that a, a satellite scatterometer can measure winds at pretty high resolution.
Mhm.
So we could anticipate a next generation maybe getting 5 kilometer resolution on winds, but those are really relative winds. But
Yes.
currents are harder to measure and so might have a coarser resolution.
Uh-huh.
And so you have a relative wind that's pretty high accuracy. And if you just need the relative wind, then that's what you've measured. But if you need to know the currents as well, then you might have to um, average or filter to a coarser resolution. And so it's interesting to think about how these types of diagnostics might be used um, in a situation where you have different resolutions for the relative wind and for the currents, and I guess therefore for the wind alone.
Yes.
I don't know if you
So
thought about that.
yeah, so this thinking about this resolution, I have worked on the resolution mismatch a little bit,
Mhm,
on my PhD work as well. So we can break the part that are coming from different components, like what is the resolution of the atmosphere and what is the resolution of the ocean. So what happens if there is a resolution mismatch? So I think we can look into those components
mhm,
individually and break down into what is coming from the unresolved parts and what is coming from the resolved parts from each of these atmospheric and oceanic components, and then see and maybe try to fill in the gaps wherever we are missing the resolutions. Yeah.
That would be very interesting. Well, I'll make one more call for other questions. Mome has his hand up.
Hello. Nice talk. Regarding the discussion you just had, to like overcome this like gap or like the discrepancy in resolution of atmosphere and ocean, basically would need a prediction of your energy cascade slopes, right? So
Yes, yes, right.
you have to do some extrapolation.
Yes,
First of all, you have to know how well your model, if you're in a model, resolves this cascade, and then how you
yes,
go beyond that. Or
right.
for remote sensing, in the same discussion, right? You have to know your filter, right? We have the discussion on SWOT, right? You have to know how well your filter behaves and what
Yeah.
that is. So you basically getting into spectral slope prediction there.
Yes. Yes, actually, this is one of the property that we have used in this getting the first order approximation here. So this ultraviolet scale locality is the assumption, or it's the property, not assumption, it's a property. It's where we say that the information, the influence on the unresolved or the subgrid scale part is coming from the resolved part, and the interaction is local in space. So whatever is in the wave numbers very far away from the resolved scale is very small. So, and for that there is the spectral slope. So the more steeper the spectral slope is, the more higher influence that the more local in space the interaction is. So, but it is enough to say that the scale interaction is local when the spectral slope is steeper than -1. 1 - 1 or steeper. Yeah.
Yeah, I mean, then there's just a technical problem of estimating spectral slopes for relatively small areas. But you're making, yeah, there need to be more assumptions made if you want to predict slopes for like, yeah, you're getting into sampling issues, I think. But yeah, anyway, we can talk about this later.
Yeah. Yeah. Yeah, I agree with that. So it's the opposite. We know the spectral slope, and then I'm getting the expression based on the information that I already know the spectral slope. But there may be cases when we don't know the spectral slope, and we don't know how the spectral slope looks like, and we may not be able to use this expression.
Yeah,
Yeah.
yeah, right.
Rick Danielson has his hand up.
Yeah, hi. Shikhar, nice talk. I appreciate it. I'm just wondering about some of the, not spectral slopes so much as Mome has brought up, but questions of the ability of say altimetry or a quickscat types platform to resolve down to a scale that has an influence of the subgrid, the subscale processes in some emergent sense, in some what you detect down to a certain scale is a function of what you can't detect in a sense. So is there a way to back up or sort of reverse engineer the subgrid scale processes from where you decide your cutoff is? So it's a function also of the filtering process of the platform, but ultimately you want to see the signal of something at a scale that you can't directly observe, or at least you can only observe the influence of those scales. So is there? I mean, I'm speaking, I guess, of the different approaches. I love it. I love that you've focused on the physics, that you've been able to capture more of the physics in your approach. But there is this coming back to the correlations, this question of how do we use the data? How do we use the correlations to back up to the physics?
Yeah, I'm not sure how to answer this question. I think I lack knowledge on how the samplings, how the observations, and how things are done there. But yes, the only thing that I can say is that we can infer about the unresolved, what is happening about the unresolved scales from the spectral slope if we already know the spectral slope from theory or from observations, and we can give some information about that. But other than that, I don't think I have answer to your question. Maybe.
I guess to rephrase it a bit, I'm not sure I believe you don't have the expertise, but to rephrase it a bit, altimetry gives you a pattern of the eddies and strain features, but that's really strongly dependent on the sampling.
Yes.
So there is a large difference in these patterns as a function of the number of altimeters, or the average the period over which you can construct your gridded field. And I guess the question might be, first, whether those pattern changes are a significant influence on the transfers of the coupling processes.
Yeah, I think it will affect. So so based on like how the gradients of the ocean currents that we obtain from the altimeter look like, it will affect the estimation of the coupling of the in this case the momentum transfer. So so in that case, I would say that I think we can only be confident about these energy transfers up to the scales that we are confident about. So let's say about the mesoscales, because it is a slow process, and we have a very good confidence upon that the mesoscale features will definitely look like this. Then upon what the flow features at higher frequency inertial scales or submesoscales smaller will look like. So I think in the global scale, we can be more confident on these scales where we are resolving, but we can also, I think, like with the missions like Odyssey, S-Mode, and SWOT, we have a local coverage. We are confident on the local flow features, and I think we can, if we can't say about what is happening globally, I think we can have a good estimate of what is happening locally there, based on these measurements locally. So yeah, I don't know if I answered your questions well, but
Yeah, it's fine. Let me just thank you also for emphasizing strain here. This is something that the community, I think, appreciates. Thank you.
yes, I also feel that we have been looking into the coupling coefficients of the curl, and when we are looking at the coupling coefficient of the straining part, we think about the divergence, which is only the diagonal part of the strain. So we are looking at the coupling coefficient of the divergences of the wind stress and divergence of the ocean current, but it is the incomplete story. We have the non-diagonal component of this trend, which is also playing a part, which is what we are trying to show in this work. So it is actually the non-diagonal part of this strain is also playing a role in the energy transfers, maybe in other airship fluxes as well.
Okay. Thank you.
Thank you. Thank you for the question.
Great. If there are other questions, please speak up. And otherwise, this has been a really great discussion, great talk. Thank you very much.
Thank you
And
for the opportunity.
yeah. And thanks everyone for participating.